Singularity Syndicate, Episode 5, Mastering Semiconductors Perspective from Drexler, Kurzweil, Goertzel on AI and Singularity. Futuristic synth with high-tech industrial undertones. Welcome to Welcome back to Singularity Syndicate, the podcast where we delve deeply into intricate sections of artificial intelligence, advanced technologies, and profound implications for humanity's future. I'm your host Charita, and this is episode 5, an extension of our previous exploration into semiconductors, AI hardware, and India's burgeoning role in chip design. Today, we elevate the discourse by framing the mastery of semiconductors through profound theoretical frameworks. Eric Drexler, Ray Kurzweil, and Ben Goertzel, seminal thinkers whose visions of the technological singularity underscore the pivotal role of semiconductor advancements. Drexler's molecular nanotechnology paradigms, Kurzweil's exponential computational scaling laws, and Goertzel's decentralized AGI architectures all converge on semiconductors as the enabling substrate for superintelligent systems. We'll dissect must learn technical topics with rigorous detail, survey and expand array of influential works, seminal research papers, and comprehensive learning sources, all infused with their groundbreaking insights. Prepare for an exhaustive technical dense journey. Let's ignite those synaptic circuits and propel your understanding to the depths. Why learn semiconductors? Semiconductors represent the quintessential enabling technology of the modern era, serving as the physical embodiment of the computational prowess that underpins artificial intelligence, quantum simulations, and inexorable match towards the technological singularity, a hypothetical inflection point where artificial intelligence ASI transcend human cognitive boundaries, initiating recursive self improvement cycles that yield exponential technical acceleration. To appreciate the imperative of mastering semiconductors, we must interrogate this through lens of three visionary pioneers, each offering nuanced, technically grounded perspective. Eric Drexler, often hailed as the progenitor of molecular nanotechnology, in his foundational treatise Engines of Creation 1986, posits a paradigm where atomically precise manufacturing (APM) leverages programmable matter to construct complex structures at nanoscale. Semiconductors in Drexler's framework are indispensable as the computational backbone for orchestrating these nanosystems. Consider the scaling requirements to simulate and control molecular assemblers. One requires processors capable of handling quantum mechanical simulations via densely functional theory (DFT) approximations, where Hartree-Fock equations and Kohn-Sham orbitals demand teraflop of compute density. Without advancements in semiconductor lithography, such as sub 2 nanometer gate lengths enabled by high NA EUV systems, Drexler's vision of mechanosynthesis involving mechanochemical reactions with activation energies on the order of zero point 0.1 to 1 eV remains computationally infeasible. Learning semiconductors thus equips one to engineer the hardware software symbiosis necessary for realizing Drexler's grey goo safeguards and productive nanosystems, mitigating existential risks through precise control algorithms. Ray Kurzweil, in his magnum opus, The Singularity is Near 2005, and its 2024 sequel, The Singularity is Nearer, articulates the law of accelerating returns, a meta law describing how technological paradigms evolve at double exponential rates quantified as dp by dt p raised to power k, where k is greater than 1, with P representing performance matrix like flops per watt. Semiconductors epitomize this through Moore's law, which Kurzweil extends beyond planar scalar to 3D architectures and optical interconnects. Technically, this involves Dennard's scaling breakdown post 2005, where power density necessitates innovations like high K dielectrics and strained silicon channels to maintain performance while curbing leakage currents via Fowler NORDEM tunneling models. Kurzweil forecast AGI achieving Turing test parity by 2029, predicated on chips reaching 10 raised to power 18 flops per 2025 by 2025, enabling human brain equivalence at 10 raised to power 16 synaptic operations per second. Mastering semiconductors allows one to critically evaluate and contribute to these timelines, optimizing for von Neumann bottlenecks through in-memory computing paradigms like resistive RAM, crossbars for matrix vector multiplications and neural networks. Ben Goertzel, architect of the OpenCog framework and founder of Singularity Net, advocates for a decentralized beneficial AGI ecosystem, where singularity emerges from collaborative open source intelligence amplification rather than monolithic systems. In Goertzel's view, semiconductor facilitates this via specialized hardware for probabilistic inference engines, such as those implementing Markov logic in networks or Bayesian hypergraphs for meta-learning. His atom space knowledge representation grounded in Hyperon logic demands chips with low latency tensor processing unit capable of handling sparse matrix operations with O n log n complexity via proximate nearest neighbor searches. Goertzel optimistic timeline singularity within a decade hinges on semiconductor driven edge computing for distributed AGI, incorporating homomorphic encryption to preserve privacy in federated learning scenarios. By delving into semiconductors, one can design ethical AI hardware such as neuromorphic chips emulating spiking neural networks, with leaky integrate and fire neuron models ensuring alignment with human values amid rapid intelligence explosions. In synthesis, these perspectives converge. Semiconductors are not merely components but substrate for transcending biological limitations, demanding rigorous study to navigate the singularity opportunities and perils. Core topics to master through their lenses. To achieve technical proficiency, we must dissect core semiconductor product topics with exhaustive detail interwoven with the pioneer frameworks. This segment expands into subdomain incorporating mathematical formalizations and engineering principles. Semiconductor fundamentals and device physics. Begin with band theory, where the Schrödinger equation governs electron wave functions and periodic potentials leading to band gap engineering. Drexler's emphasis doping profiles N-type with phosphorus donors, P-type with boron acceptors for fabricating nanoscale transistors. Explore carrier transport via drift diffusion models and quantum confinement effects in 2D materials like graphene, where Dirac cones yield realistic electron behaviors. Chip fabrication and process integration. Delve into CMOS process flows including ion implantation, rapid thermal annealing, and chemical mechanical planarization. Kurzweil's exponential scaling ties to lithography, extreme ultraviolet enable sub 5 nanometer features via multi-patterning, combating diffraction limits per Rayleigh criterion. Study 3D NAND stacking with greater than 200 layers, employing atomic deposition for conformal HFO2 films and heterogeneous integration via CU-CU hybrid bonding with pitch less than 1 micrometer. AI hardware design and architectures focus on domain-specific accelerators. Goertzel AGI requires systolic arrays for tensor contractions in deep learning, optimized for gem operations with throughput greater than 10 teraflops. Learn analog digital hybrids like memristors based crossbars for in situ training via Hebbian learning rules, reducing von Neumann shuttle energy. Incorporate error correction for stochastic computing with bit flip probabilities, model probabilities, probabilistic logics, advanced materials, and beyond silicon paradigms. Beyond silicon, explore wide bandgap semiconductors like silicon carbide for high voltage devices and GaN HEMTs and 2DGE TEG mobilities. Drexler Nanotech envisions carbon nanotubes or graphene nanoribbons for ballistic transport, minimizing scattering via mean free paths equal to 1 micrometer. Study phase change materials PCM like GESPTE for non-volatile memory with switching energies. EDA tools, simulation and verification. Proficiency in electronic design automation is crucial. Use SPICE for transient analysis. Laws via Newton-Raphson iterations and TCAD tools like Satanarus for finite element modeling of dopant diffusion. Kurzweil simulations for brain uploading demand quantum accurate models, incorporating density matrix, renormalizing group for many body effects. India specific context and global ecosystems. Analyze India's semiconductor mission with 76,000 crore allocation, targeting 3 nanometer nodes via collaborations like Tata PSMC. Goertzel decentralized vision aligns with India's fabless design centers in Bangalore. Fostering IP and RISC-V architectures, SoC integration. Examine supply chain resilience, modeling disruption via graph theory. Emerging frontiers, quantum and optical integration. Extend to quantum dots for qubits with coherence times greater than 100 microseconds via Purcell enhancement and silicon photonics for optical interconnects. Drexler's APM intersects with quantum error correction codes like surface codes, ethical and risk mitigation. Incorporate alignment techniques such as formal verification of AI hardware using model checking to prevent unintended behaviors in ASI reference. Top blogs to follow: Straits Research, STRAITS Straits Research, Siemens Thought Leadership, STM Microelectronics blog, Averroes AI, Dasenic, Medium Technical Series, SemiWiki, Van X Semiconductor Insights, JAMA Software, Fabricated Knowledge, EE Times, IEEE Blogs, Anand Archives, and Semi Engineering. Must read research papers. For core device and materials paper, Human Machine Collaboration for Improving Semiconductor Process, Nature 2023. AI in Semiconductor Industry, ResearchGate 2024. AI Semiconductor Integration. Silicon Squeeze, AI Impact on Semiconductor Industry, the Intersection of AI and Semiconductors, Microchip USA 2025. Best learning sources, online platform and courses, Coursera, EDX offerings on VLSI design covering Verilog, HDL for FSM and RTL synthesis, Drexler inspired and nanotech modules on MIT courseware, open courseware including molecular dynamics with lamps, industry training programs, semi-university for advanced packaging, teaching CU, pillar bumping and TSV through silicon via etching. NXP AI Academy for embedded model, optimizing for ARM Cortex-M, CMSIS NN libraries, simulation modeling tools, databases and repositories, communities and forums, reports and white papers, books and monographs, hands-on lab, conferences and webinars. Tying it to India and Singularity, a holistic synthesis. India's semiconductor landscape with ISM ecosystem incentivizes and 3 nanometer R&D hubs exemplifies a convergence of Drexler nanoscale precision, Kurzweil acceleration and Goertzel decentralization. Technically, this involves indigenizing supply chains for rare earth dopants and photomasks, modeling economic impacts via input and output matrices. In singularity context, India's contribution could democratize ASI success, access, mitigating centralization risks while amplifying exponential growth. That concludes this exhaustive episode 5, enriched by profound insights of Drexler, Kurzweil, and Goertzel. Mastering semiconductors at this technical depth position you as an architect of singularity. If you're ready to dive deeper, I can provide bespoke learning roadmap for GitHub repository for advanced semiconductor simulations. Thank you for joining this intellectual odyssey. Share widely, subscribe for more, and remember the future is etched in silicon. I'm Charita signing off. Keep engineering the extraordinary.